Now we will look at different types of fluid flows. Flow conditions can vary point to point and time to time. That means they vary spatially and temporally. Spatial variation. We can identify two types of flows. One is the uniform flow. Uniform flow. Velocity at a given instant is the same in the magnitude and direction at every point in the flow. Now you can think what is non-uniform flow. Non-uniform flow gives changing velocities at various points. Let us look at the temporal variation. Steady and unsteady flows are the two types of a flow in temporal variation. Under the steady flow, this flow condition tells us the velocity, pressure, and cross section of the stream may vary from point to point but do not change with time. Now, the unsteady flow is flow conditions vary with time in this type of flow. Now, we can formulate another four types of flow conditions: steady uniform flow, steady non-uniform flow, unsteady uniform flow, and unsteady non-uniform flow by combining the previous four flow conditions. Then we can have real and ideal fluids. Real fluid flows have shear stresses. Therefore, they have a velocity variation across the cross section. However, ideal fluid flows do not have any shear stresses. Thus, there is no velocity variation across the cross section. Now, please refer the image and understand the velocity distribution. Then we have compressible and incompressible flows. We know all fluids are compressible so that the density changes with pressure. But under the steady flow conditions, if the density changes are small enough, we call them incompressible fluid flows. In our module, we are more focusing on incompressible fluid flows. Now, let us mathematically express the conveyance of fluid flow. If we consider the stream tube, we know we have flow from two surfaces. They are the cross-sectional surfaces. Let us consider a small surface area from the cross-sectional area, say surface 1. Now that small area is delta A. We know the flow through this small area is delta Q is equal to V delta A. Therefore, we can find the total flow rate by integrating across the area. That is, Q is equal to areal integration, that is over surface 1 VdA. That comes to discharge is equal to mean velocity into area. We can find the flow rate to the surface 2 as well. Now, let us recall the mass continuity or continuity law. It is assuming the control volume remains constant. We can say that in any time interval, the mass entering the control volume must be balanced by the mass leaving the control volume. Simply, it says matter can neither be created nor be destroyed. Thus, m dot 1 is equal to m dot 2. Now, this dot stands for the rate. I hope you know. So, we can expand this. M1 dot is rho Q1. Please look into the density. Density is equal to mass divided by volume. So, if you won't get rate of mass, that is density into the flow rate. So, we can have rho 1 Q1 as the M1 dot, rho 2 Q2 as the M2 dot, and we know we are dealing with incompressible liquids, so rho cancels out and we have Q1 is equal to Q2. That means flow in is equal to flow out. Now we can obtain this using the vector notation as well. Please go through these slides and understand the vector notation. The last topic of this section, branching control volumes. The continuity equation only looks at whatever matter it is entering to the control volume and whatever matter leaving the control volume. Therefore, it can be simply applied to branching networks. Now refer the figure. We can find out that the entering flow rate, that is Q1, has to be equal to the leaving flow rates. They are Q2 and Q3. So Q1 is equal to Q2 plus Q3. Now, let us look at three different cases in calculating flow rates. Uniform velocity distribution, example is a free jet. Please look at the calculation and identify the analyzing techniques. This is rather easy. You know Q is equal to integration of VdA. Now the case 2 is linear triangular velocity distribution. Case 3 is the parabolic velocity distribution, that is inside a pipe. Now, I'm sure you can follow these slides and identify and understand the solution techniques. Basically, if we go through this method, it considers the simple equation for the parabola, because the velocity distribution is a parabola and you're trying to find what is A, B and C for the parabola. Now that concludes our session for the introduction of flows.